In this video, we're going to learn how to evaluate logarithms whose base is neither 10 nor e, which are those two buttons you have on your calculator. Then we're going to use the change of base formula, which reads log base b of m is equal to log base a of m over log base a of b, essentially changing the base to wherever we want the base to be while putting the inside of the logarithm in the numerator logarithm and the base of the logarithm into the denominator's logarithm. Now let me show you where this formula comes from because it's not too hard to show. First, we're going to take the log base a of each side of this equation. By the way, this equation comes from just setting y equal to log base b of m. So I have log base a of b to the y power is equal to log base a of m. Next up, I'm going to use the property where I'll move that power to the front of the logarithm. So I'll have y log base a of b is equal to log base a of m. Now to solve this for y, I can divide each side by log base a of b. So y is now equal to log base a of m over log base a of b. And like I established at the start, y is equal to log base b of m. So I end up having log base b of m is equal to log base a of m over log base a of b. So that is where that formula comes from. There are a few other ways to explain it, but here's just one of them. So this just means that on our calculator, if we want to evaluate a logarithm, we'll take the log of the inside number over the log of the base. And we can use either log or natural log. And I'll show you what it looks like with this first example whenever you use either one. So I'm going to start with using the change of base formula and a calculator, which I have handy over here. We're going to evaluate each logarithm and round our answers to 3 decimal places. So to evaluate log of base 5 of 89, I'm going to write that as log of 89 over log of 5. Now I could have also done natural log of 89 over natural log of 5, and I'm going to show you the difference in this next step. So let's say we take the log of 89. That gives me 1.9. I'm going to write out that entire decimal. 1.949390007 over log of 5, which is 0.6989700043. Now, if I did this with the natural log, which I'll put my calculator over here to get it out the way, I'll get natural log of 89, which is a bit bigger. 4.48863637 divided by natural log of 5, which is also a bit bigger than the log of 5. But their ratio that I get should equal the same number. If I put in 1.949390007 divided by 0.6989700007 0.00043, I get 2.788, which if I'm rounding to 3 decimal places should be 789. And then doing the natural log ratio, I would have 4.488, 63637 divided by 1.6094 37912, which when rounded to 3 decimal places is also 2.789. So we can say that this logarithm is approximately 2.789. Now, to save you a little time in the future, you don't have to go about this entire route. You can just type into your calculator log of 89 divided by log of 5. It would also tell you 2.789, or you can use natural log, and they'll both tell you the exact same number. But I just wanted to show you what happens when you use either one fully, that the numbers do look different, but the ratio will always give you the correct number for your logarithm. So if I look over here at log of the square root of 2 of the square root of 5, I can write that as log of the square root of 5 over log of the square root of 2. Now I could plug that to my calculator, but also notice they're both in square roots. So I could write this as 1/2 log of 5 divided by 1/2 log of 2. Cancel out the 1/2s, and it turns out that this is just equivalent to log of 5 over log of 2. So if I typed in log of 5 divided by log of 2, I would get approximately 2.321. Oh, sorry, 322 when I round correctly. And if I happen to have kept them as square roots, I would have log of the square root of 5 divided by the log of the square root of 2, which would also give me 2.322. So either or, but you can use those logarithmic properties to maybe make it easier to plug it into your calculator. For this one down here, I'm going to use the natural log ratio instead of the log, just to try out something different. But now this will give me natural log of e over the natural log of pi, which I actually have a property I can use. The natural log of e, the base of a natural log is e, the inside is e, so if they match, that should just equal 1. So I just need to type in 1 over the natural log of pi. And that gives me approximately 0.87 and then 4. Now, for this last problem, I'm actually not going to use the calculator. I want to show you another way you can evaluate logs where you know they might have a common base. So if I have log base 8 of 32, I know that they're both powers of 2. So I can actually rewrite this as log base anything, like my thing said earlier. I could pick log base 2 of 32 and divide that by log base 2 of 8. Now, 8 is 2 to the 3rd power, so log base 2 of 8 should be 3. And 32 is 2 to the 5th power, so log base 2 of 32 should be 5. So this is equal to 5/3. But if you must put it as a decimal, that should be 1.667. And if I were to plug this in with a calculator, a different way, like log of 32 divided by log of 8. I did that without a calculator, but now, plugging it in, I'll get that 1.667, like I've already calculated. And that is how you evaluate logarithms whose base is neither 10 nor e.